Department of Electrical and Computer Engineering, Kansas State University, USA. We have Professor Sanjoy Das from Department of Electrical and Computer Engineering, Kansas State University, USA. We have Professor Sanjoy Das. So before I invite Sir for delivering talk, so let me introduce about Sir. Sir has completed his PhD in Electrical and Computer Engineering from Louisiana State University in 1994 and received postdoctoral training at the University of California, Berkeley. He worked for several years in the industry before joining Kansas State University in 2001. Sir has over 130 publications in international journals, books, and conference proceedings. His research has so far been sponsored by several major grants from the National Science Foundation, from the Office of Naval Research, and the US Department of Agriculture, as well as some smaller ones. Professor Das is primarily interested in biological inspired computing. He is investigating the applications of these algorithms for specific optimization problems in plant genomics, in collaboration with Professor Welch, and in distribution system modeling in collaboration with Professor Power. Sir has received Faculty Award for recognition of outstanding leadership from the Kansas State Engineering Student Council in April 2006. Sir has been also involved in organizing several international conferences and symposiums. Today, Professor Das will be delivering a talk on multi-agent learning. So with this brief introduction, I invite Sir to take over the. Thank you.
Hello. Is it on?
Hello. Hello. Hello.
Hello. Is it on now? Can everyone hear me? Yes. Okay, great. So thank you so much for the wonderful introduction, several times, and and good morning to you all. So my talk shall be on learning and coordination in multi-agent systems, and just a brief bio, most of which was covered by him. So that's my education and experience. And my research interests have actually changed quite a bit in recent years. So I work mostly with multi-agent systems and algorithmic game theory and quantum computing, optimization theory and algorithms, and the applications that I explore are in computational genomics, smart grid, sustainability, communication, and networks. And I have divided my lecture into two parts. The part one is we'll focus on single agents, reinforcement learning in single agents. And then in part 2, we shall go to multi-agent systems and how reinforcement learning happens in that environment. So now, as you have already realized, this is different from the other talks that have so far taken place. It's not directly connected to antenna, but the thing is, this is the day of cross-disciplinary research. And I have worked in the past with the conference chair, Professor Patnaik, and we work together very closely, in fact. And there are a lot of scope for applying these techniques to applications in antenna. And so it's to our mutual benefit. New techniques, better techniques can be used for antenna design, and at the same time, from our perspective, we are exploring new applications, and with each different application, we get a new twist, which also leads to further theoretical research in our area. Thanks. So part 1, what we shall do is I shall explain what's just a very broad picture of what's reinforcement learning, and then I shall go a little more formal. We shall look at what's a Markov decision process, and then what exactly is an agent's goal there. Values and policies, many of you probably know what's Bellman's equations, that has to do with optimal adaptive control. And as a matter of fact, reinforcement learning and optimal control share the same roots, but the approaches taken have digressed. And then we shall do, okay, value iteration is the basic algorithm that's based on Bellman's equation, and it's used for reinforcement learning. Then we shall go to a very popular algorithm called Q-learning. I shall show one particular application of this Q-learning algorithm by my research group to shipboard power system reconfiguration. At the end, I was planning to show you a MATLAB demo, at the end of part 1, that is, but we shall move this to at the end of part 2. Now, since I'm aware of the fact that we come from slightly different backgrounds, treat this talk as more like a tutorial on reinforcement learning, and instead of going deep into certain aspects, my intention is to give you a broad overview and some, for the benefit of the students here, I'm aware that there are a lot of undergraduate and postgraduate students, masters and PhD students, and so for their benefit, I shall go very slowly, and it's almost like a course. Treat it like a classroom lecture or something. Okay, so what is reinforcement learning? I guess you need an introduction to what's an agent. Don't have a slide for that, but a neural network would be considered to be an agent. An agent is basically a algorithm that is equipped to make some decision making. A neural network can do classification or regression tasks. So a neural network can be perceived to be an agent too. So X is the input to the agent, and Y is the output of the agent. Now, what is reinforcement learning? In machine learning, we typically classify all learning tasks into 3 categories: unsupervised learning, supervised learning, and reinforcement learning. So here's unsupervised learning. In unsupervised learning, the agent only receives inputs and no other feedback, just the inputs. And from the input, it somehow learns certain features, hidden features about the input data, and trains itself to give the correct output. Examples of unsupervised learning are PCA, self-organizing maps, dimension reduction, clustering, so on. And just to, if in case you don't know what's unsupervised learning, here's an example. Clustering is a typical example of unsupervised learning. In clustering, okay, so this is the input space. And the agent, which could be a neural network, by the way, is presented with each of these points is a data in the input space. And then the agent learns to somehow, in some good way, to cluster the inputs. So clustering, so it divides the input space into different regions. So this is a typical example of unsupervised learning. You don't need any other feedback or any other input other than samples of the input space itself. Then at the other extreme, you have supervised learning. And in supervised learning, I've been attending some of the talks, and many of you have actually used artificial neural networks and radial basis function networks in your research. So, so those are examples of supervised learning algorithms. And in supervised learning algorithms, what happens is, this is the agent, which is the learner, and in addition to the inputs, X, the agent also receives an error signal. It produces an output, and then there's a supervisor, which presents the agent with the error. And then the agent, for instance, could learn to minimize the mean square error as you do in backpropagation or radial basis function networks. So supervised learning is typically there are two tasks, regression and classification. Examples of supervised learning are, like I said, multi-layer perceptrons, backpropagation. Okay, now reinforcement learning is somewhere between the two. Now this is unsupervised learning. It's just the input and the output and the agent itself. At the other extreme, you have supervised learning, where you have X and Y, the inputs and the outputs, but then you have a supervisor that explicitly helps the agent get trained to perform its tasks better and better. In reinforcement learning, what you have is, it's an intermediate situation. There is the input and the output, and instead of error, instead of a supervisor that presents the agent with the actual error, telling, okay, this is exactly what you should have done, the agent receives from the environment a reinforcement signal. Okay, now let me explain this. So an example of reinforcement learning would be game playing. Now chess is typically reinforcement learning. Learning doesn't work so well with chess, but there are other games requiring a lot of thought, like backgammon. I understand that backgammon is not particularly popular in India, but nevertheless, it's a game that requires a lot of thinking. But you also have to roll a die, so there is a probabilistic component to backgammon. And reinforcement learning, neural networks trained with reinforcement learning algorithms have been known to do exceptionally well with that task. So I'll use this example as to tell you what's the reinforcement signal. So what happens is, let's say we are playing a game of backgammon. What's this? There is no such thing as error. In chess, if you move a pawn or if you move the queen or the knight, there's no way you can say that, okay, this is the correct move, right? Or this is the, what's the error between the correct move and your move. There's no such, you cannot quantify that. But at the end, whether you win or you lose, that's the reinforcement signal, right? So if this agent is trying to play a game of chess, then the reinforcement signal would be 0 until at the end of the game. And then it'll know whether all its moves were good moves or bad moves. or maybe in how many moves it won. Based on that, it would be able to quantify its goodness of its outputs. So that's the nature of the reinforcement signal. It's not a mean square error, it doesn't carry that much information, but just basic information of how good or how bad it's performing overall. Well, it depends on the perspective. Typically, this is very, very slow because you have to train it over and over and over again. And then there are a slew of algorithms, and there are certain other things that you have to look at when you are developing a reinforcement learning agent that you normally don't even think of in supervised or unsupervised learning. So I would say it's more, in a manner of speaking, more complicated than either supervised or unsupervised. Okay, so let's go a little deeper into this and see how the agent works. So this is the agent and this is the environment. And we shall see how things happen with time. Time here is discrete and integral. So we go t equals 0, 1, 2, 3, 4, and so on. Discrete time. And the environment is something that the agent works upon, and the environment can exist in one of several discrete states. In a game of chess, the exact position of the board would be a state, for instance. Okay, and so at time t, we denote the state of the environment as S sub t. And this state is sensed by the agent. That's the first step that happens. The agent senses the state, and then, based on the state, the agent performs an action. Again, subscript t because it's happening at time t. So the agent performs an action based on st. It performs an action a of t, and that action is acted upon the environment. And this action will result in some change to the environment, due to which the environment will eventually change its state. So, meanwhile, what happens is, again, at the same time t, once the agent applies the action a of t to the environment returns the reinforcement signal. And it might not be instantaneous. You could also have a delayed reinforcement signal, as in a game of chess. It's only at the very end will you know if you won the game or lost the game. Until then, the reinforcement signal would simply be 0. Then now, we see a time increment here. At time t plus 1, the environment from state S of t, based upon the action a of t that the agent carried out, it transitions to a new state, S t plus 1. And at the same time, during this whole process, the agent learns something. It's like one step of backpropagation, similar to that. Let's go a little deeper into this. Okay, so the environment is modeled as a Markov decision process. So MDP is a Markov decision process. Many of you know what's Markov chain, discrete Markov chain or Markov process. MDP is an extension of Markov process. So it's defined as a 4-tuple, a set of states S. I told you there's a set of states. Environment can exist in a state at any single time. And then you have a set of actions. The set of actions is something that can be carried out upon the environment by the agent. In chess, it would be advancing the pawn or the knight or whatever. So these are the sets of actions. Note that the actions, this transition, once you have a state and then the agent performs an action, the transition to a next state is not deterministic. It's a Markov model. So it's probabilistic in nature. You don't see that in chess because if you move a pawn, well, you've moved a pawn and you know exactly what the next state of the environment, the board is going to be. But if you, let's say you're playing a game of carom, right, and there your aim is to put the red dot on the hole, but it might not happen, right? So there's a certain probability of success, and otherwise something else could happen. So the state of the environment after you take your action is probabilistic. And so we have a probability distribution. Probability, given a state and an action, what's the probability of transitioning to another state? And we denote that as P of S, comma, A, comma, S prime. S prime is the next state. So this is the current state, S. A is the action that the agent carried out upon the environment, and S prime is one of the possible next states, and P of the whole thing gives you that probability. And then you have a reinforcement signal. So given a state and an action, you have a certain reinforcement signal. And this is what we denote the reinforcement signal as. R of S comma A. This is the current state and then the action taken. Okay, now here's a little example. We have two states. In some application, we have two states, L and R. And there are two possible actions that we can carry out on this environment, and they are red and blue. So from this state L, suppose the action is B, blue, then there's a 0.8 probability that the transition will be from L to R. So the next state will be R. And so this is the transition probability, P of L, comma, B, comma, R. This is the next state, R. And on the other hand, even after this action, blue, is carried out, the environment could remain in left state, in which case the probability of that is P of L, comma, B, comma, L, the next state, which is 0.2. And you need to make sure that the two add up to 1. 0.8 plus 0.2 is 1. Likewise, if the action is of blue, if the action were red, then we would have another set of transition probabilities here. And this is all from the initial state L. If the initial state were, okay, this is all possible transitions from L. And on the other hand, if we start from right, then we can define another set of probabilities. Okay. Which one?
Out of several decisions, which signal will be generated? Which is optimized signal or?
You mean the
yes.
reinforcement signal?
Yes.
Generally, that's predetermined. Before you starting the learning process, that's a good question. The reinforcement signal is determined. A priori. So it's not, well, different reinforcement signals, the selection of reinforcement signal would obviously influence the quality of the learning. But at the same time, it's something that we, at least I, in my research, don't normally play around that much with. It's the algorithm. So based on this, this is one of the information that is received by the agent. And then internally, the agent does something. And that's what we focus on. So it's hard to say what is optimal when it comes to this feedback signal. Okay, now that was a static viewpoint. Now let's look at it from a dynamic viewpoint. through time. So this arrow denotes the progress of time, which is discrete, like I said, 1, 2, 3, 4, that's how we do it for convenience. And then this is the state at one particular time instant, L, and then the action that was actually taken was red, and it then actually did transition to R, and then the next action that was taken was B, transition to R again, and then the action here was B, blue, and then the transition this time, same action, but it transitions to L, another state. And so this is what's happening. So this is the agent, this is the environment, and we saw this picture earlier. And so at time t minus 1, the environment was in this state, S of t minus 1, then the action that was taken upon it was A of t minus 1, it transitioned to st, then action AT resulted in st plus 1, action AT plus 1 resulted in S of t plus 2, and so on. And in each step, the agent updates its parameters. So in this case, now this is directly addressing your question. So what's the agent's goal here? Obviously, the agent's ultimate goal is informally to maximize the reinforcement signal, right? That's the whole idea. One way to do it is look at a time window, t. Then we are in current time is t0. And we look at the average reward from t0 to t0 plus t and divided by t. That's the average. We call this the reward now, and this is the average reward. And one possible way to describe our goal is to minimize this. But that's not what we do, as I'll explain a bit later. What we do instead is this, a discounted reward. And that's like this. So the discounted reward is like this. Okay, this is the reinforcement signal at time t0, t of 0, current time. And then we have a discount factor, gamma, and this is gamma times the reward in the one step into the future. Then this is the reinforcement signal 2 steps into the future. And we multiply it with gamma squared, and then gamma cubed of r t0 plus 3, and so on, until infinity. And this converges because as we go further and further to the right, we'll get this gamma, the exponent of gamma will increase. And since gamma is less than 1, it'll get smaller and smaller. So this is called the discounted reward. At any time t0, the goal of the agent is to minimize this. Why this is, okay, there are actually multiple reasons for this. One is, there's a very theoretical reason for this, and that comes from Bannach's fixed point theorem, which says that, which guarantees convergence to a fixed point if gamma is less than 1. That aside, there are other reasons too, and wait a second. So why is it, so treat these as weights. So this is the instantaneous reinforcement that you're receiving. And then this one step into the future, it's weighed a little less, right? Gamma, typical value of gamma could be 0.9. So this is 90% of this one, as important as this one. Why so? Because one reason is uncertainty. We're not sure, because it's a probabilistic environment, we're not sure exactly what the next state would be, right? And so we're not sure what the future reward actually, the future reinforcement signal actually would be. So as you go further and further into the future, it becomes more and more uncertain. So it's not a good idea to weigh these as much as this one, right? And so that's one reason why we do it this way. Does that answer your question? Gamma is simply a parameter, a learning parameter. Just like in map propagation network, you have epsilon, or the learning rate, or the momentum rate. So it's a parameter. Pardon me? it can be seen of as a weight factor. There is also a probabilistic interpretation of this. I will not get into that. There is a probabilistic interpretation of gamma 2. 0.9 is the probability that this would actually, you would get into a new state. Otherwise, 1 minus gamma is the probability that after this, the environment would terminate. So that's yet another reason. But for our purpose here, I need to tell you that when gamma is less than 1, then the learning algorithm that we shall see later will converge. It guarantees convergence. And the other thing is, from a philosophical standpoint, you're not sure what this one is. In fact, this signal here, reinforcement signal, should be replaced with expected reinforcement signal, because you're not sure. This is also an expectation. This is an expectation. Only this one is not unexpected. It's the real reinforcement that you receive at that time. So that's why the further we go to the future, the less we place weights on. And so let's look at it like this. My goal here is to somehow cast this in the form of a recursive equation. So this is the time instant. We are in time instant t, and this is what the future possibly would look like. And so this is the reward signal, and our goal is to maximize this reward signal, right? RT plus gamma times RT plus 1, and gamma squared times RT plus 2, gamma cubed times RT plus 3, and so on. Now, at the next time instant, RT plus 1, this is the current time, T plus 1. So now our this is current, and this is 1 time step into the future, this is 2 times step into the future, and so on. This is the total reward signal that we want to maximize. Note that now gamma has disappeared from here. This one had gamma square earlier. Now it's simply gamma. This was gamma cubed, now it's gamma squared. And so this is the discounted reward at time t plus 1. At time t plus 2, this is what it looks like. Now, from this, let's work backwards. So this is RT plus 2 plus gamma RT plus 3 plus other terms. At t plus 1, the reward signal can be cast in this form. RT plus 1 plus gamma times all of this. So RT plus 1 plus gamma times reward at time t plus 1. And moving one step back, at time instant t, we can rewrite the reward signal as RT plus gamma of this whole thing within parentheses, which is equal to RT plus gamma times reward at t plus 1. And so this allows us to express the reward signal as the immediate reinforcement signal plus, it's not showing the whole thing here for some reason, the immediate reinforcement signal, which is this, plus the discounted future reward. Okay, and so this is RT is the immediate reinforcement signal. So we are looking at this whole thing as the reward at time t, which is the immediate reinforcement signal plus gamma times future reward signal. So that's the goal of the agent, which is to maximize this. And I hope it's clear why we use a discount gamma, which is less than 1. Yes. As far as I know, there's no theoretical precise approach to decide that, but it's determined a priori. So once before you run the algorithm, you decide gamma. Okay, I'm going to make gamma equals 0.9. No, gamma is fixed. It's not like you're changing gamma at every time instant. Gamma is fixed. Throughout the training process, gamma is fixed. And let's assume 5.9, 8.8, something of that range. Much like you decide the training rate a priori before you start training a neural network with the backpropagation algorithm, you fix the momentum and you fix the learning rate. Or in a genetic algorithm, you fix the mutation rate and the crossover rate a priori in exactly the same manner. Here, in this situation, you fix a priori what the value of gamma would be based on, among other things, your own intuition and experience with that particular application. Okay. Now, value and policy. So these are two important terms that we come across when we deal with reinforcement learning. Am I going too slow or optimal speed or too fast or what? Is this... And one thing that happened is I don't have, yeah. Okay, let's keep this speed. I'll speed up a little bit towards the end. So policy. Policy is, it's defined as a mapping from states to action. So, okay, I'm an agent and I'm following a particular policy. So I'll sense the state of the environment, and then based on my policy that I have adopted, I choose, okay, I'm going to take this particular action. So it's the policy that decides what action to take. If you're playing a game of chess or a game of tennis or whatever, maybe your policy is an offensive policy or a defensive policy. And based on that policy, you decide what action you would take. Okay? And then, so that's policy. And how do we choose an action from a state? And the other thing that you need to know is value of a state. Each state is assigned a value. The value of a state reflects how good that particular state is. In a game of chess, if you are very close to checkmate for your opponent, then the value of that state is very good, high. Otherwise, the value of that state is low. If you are close to losing, the value of the state would be negative, and so on. Pardon me? Policy is a mapping from the set of states to the set of actions. So, oh, it's not here. So this is a set of states, right? And this is a set of actions. So policy, given a state, what action should I take?
What action should be in the next one?
Yes.
So for that one, the existing environment conditions will also be taken into consideration. So actually,
the existing environmental conditions, all of them have to be represented within the state itself. The only thing that the agent knows is the state.
Okay, that means the entire set of states shall we think of as policy?
The
entire set of states, can we think of it as policy, sir?
No, the entire set of states is something that's intrinsic
Different.
to the environment.
Yes, sir.
The action is common to both the environment. The environment receives the action and the agent applies the action. The policy is intrinsic to the agent. So once the agent sees the state of the environment, how will it decide what action to implement next will be based on the policy. So it's a mapping from a set of states S to the set of actions.
I mean, the reinforcement is depending upon the policy, I think so.
The reinforcement signal is again
it is also coming out through agent
because it's coming from the environment.
Yes, sir.
But the goal is to maximize the reinforcement signal.
Okay, sir.
So again, the reinforcement signal is not part of the policy per se.
Thank you, sir.
Okay. So once again, so policy, I hope it's clear now. A policy is a mapping from states to action. Given a particular state, the agent will decide based on the policy it has adopted what would be the next action. And the ultimate goal, we want to maximize the reward at every timestamp, right? And so one way to look at it is the one that actually maximizes the reward is called the optimal policy, as we should see later. And there was a question somewhere.
Is the value equivalent to fitness?
The value, pardon me, is the value?
Equivalent to fitness function optimization of algorithms.
The value is simply a number. For each state, you have a number. Okay, so the value, let's say we are playing a game of chess. The state of the board has a certain value to each player, right? And that value can be represented by a number. That's the value.
So it represents the...
And the higher the value, the better it is. Okay? Okay, so that's the value. And this is actually an example on how we can compute the value. For instance, let's go back to this example. We had two states, and this was the probability of transitions. And now let's assume that the reinforcement signal is 100 when we take an action R, and we land up, the environment lands up in this state R. Okay, so if it lands up in L, then the reinforcement is 0. If the action is blue, regardless of whether the next state is L or R, the reinforcement is 0. It's only when the agent applies this action R, red, and the next state becomes right, only then does the agent receive a reinforcement of 100. And let's say this is our policy. Our policy is a very simple policy. With probability 0.7, we apply action R randomly. And with probability 0.3, we apply action B, independent of the state, initial state, ST, L, or R. So what are the values of L and R based on this? Now, here's a simple example, which I hope will make it clear. Okay, so I've replaced L and R with values. So these are numbers now, which we are going to calculate. And this is the policy. With the probability of 0.7, we are doing right, and with the probability of 0.3, we are doing this action left, blue, and these are the possible reinforcements. And the rewards, these are the transitions, and the reinforcements are R equals 0, R equals 0, R equals 0, only when we're transitioning to R, and the action taken is, was it blue or? Did I say blue or? Oh, red, yeah. And so if the action was red and the next state is R, then the reinforcement signal is 100, right? And so the expected reinforcement from L is probability of R, probability of the next action being R, multiplied by, if you take R, then you could land up with this probability, the next state would be R, in which case you get a reinforcement signal of 100, or with probability of this, P, L, R, L, you still remain in which case the reinforcement signal is 0. On the other hand, from this state, if you choose this action blue, whose probability is 0.3 based on this policy, then probability of B is 0.3 multiplied by this transition probability, probability of transitioning from L to R based on B, times this into this reinforcement signal, which is 0, plus this probability, again multiplied with 0. And so that gives you 28. This is 28. So this is the expected reinforcement from L. You are in the state L, then this is the expected reinforcement. Now, expected reward from L is again computed in a similar manner, so probabilistically, and if VL and VR are the values, then this is what expression we land up with for the expected reward, which is the immediate reinforcement plus the future reinforcement. And so it is this. And so we get one equation. The value of left is this expected immediate reinforcement, which is 28, plus future reward, which is equal to this. And that is one expression that you get. And then if you, from this state, you also get another expression like this. And using this and this, we have two variables, VL and VR, and so we have a simultaneous equation. We can solve the simultaneous equation and we can get VL and VR, the actual values VL and VR. Pardon me? Yes. So VL and VR, one way to look at VL and VR is the value of the state is the expected future reward. Expected discounted future reward is the value. So that's why, look at this equation here. Value of R is the immediate expected reward you're getting from this, which we can calculate, and then we calculate what's the expected future reward, which again has to be dependent on VL and VR. Yeah, so you have, that's why you have VR on both sides. And then you solve it and you get the value of VL and VR. Now this is obviously a very, very simple situation. But when you have a much bigger situation, you have to use some kind of an algorithm to do it. Now, how do we define optimal policy and optimal value? Now, our goal is to maximize the total reward, right? Iteratively, we will maximize the total reward. And what happens is, when we maximize the total reward, we are changing our policy, and once we've met our goal, once the policy we have adopted always maximizes the reward, then we say that it's the optimal policy. And the value, as this example will show, also depends on the policy. Okay, so what's optimal policy and optimal value? Now, here's another example. Now, this is a game of chess. And this is, I'm sure you recognize this guy, Vishwanathan Anand, and he follows the optimal policy. Okay, now this is the state of the environment, the board. And for him, from this situation, it's very easy for him to win, right? So this state, if this is the policy, the value of the state is 95. And since he's the best player in the world, you cannot assign a value higher than 95 to this state. Okay, so once you are playing the optimal policy, the values of the states are the highest. Conversely, it's a little confusing if you have someone who's a novice, and many of you would recognize the what this 44 means. So this is the state, and now this person doesn't know how to play chess so well. He might land up losing, right? And so the value of this state is only 44. It's the same board, but for him, this is not the optimal policy. For if the policy is not optimal, the value of this state is actually lower than 95. On the other hand, if this is the optimal policy, the actions are the optimal actions, and each move is optimal, right? The policy is that you're following is the optimal policy. In that case, the value of the state is high. So it's kind of confusing. Optimal value defines optimal policy, and optimal policy defines optimal value. It's a little hard to impress that in just one small session, but that's what happens. Optimal value defines optimal policy. What's optimal value? The one that will produce the highest value for each state. That's the optimal policy. What's the value? Optimal value? That once you're following the optimal policy, what's the value of the state? That's the optimal value. And the optimal value is necessarily the highest possible value. Okay, so here's a little more detail. So what we denote the optimal policy is pi star. So pi star, S is a state. Pi star S, as I told you, what's a policy? A policy takes a state as an argument and produces an action, right? So S is a state, and if you're following this policy, the optimal policy pi star, then pi star of S is an action. And what action is it? It's the one that maximizes the value. This is, you carry this maximization over all possible policies, and so argmax with respect to pi of value, pi of S, gives you the optimal policy. And what's the optimal value? We denote it as V star of S, and V star of S is the highest possible value that you can possibly assign to any given state. And once again, to remind you, for this particular state, you cannot assign a value higher than 95. Because in 3 moves, this person can win the game, and no one else can win the game in fewer than 3 moves. Okay? So the highest possible value of the state is when you're playing the optimal policy. So this is the definition of optimal value. V star of S is V pi star of S. This superscript is the policy. Value depends on policy, as you obviously discovered by now. So V pi star of S, which is max of V pi of S. So you're doing the maximization. You try to maximize every state S. You find what's the maximum of the value, and that is V star of S. And so this equation, Bellman's equation, this is what it looks like. This is the cornerstone of reinforcement learning. Value of a state S using policy pi is given by this value. So let's say you have a fixed policy pi. The value of the state S given this policy pi is expected value of this. So it's equal to the immediate reinforcement signal plus discounted expected future reward. That's the value of the state. Okay, so it has 2 terms: the immediate reinforcement signal plus discounted expected. You have this probability here, right? So summation over this probabilities times the value of them. So this is a probability of transitioning from S due to this action pi S to a new state S prime. It's a probabilistic transition. So this is a probability, and you're summing it over all possible future next states S prime times the value of the next state. So this term is the expected future reward, and gamma is the discount factor, and so this defines the value of any given state. And so this, basically that's what I said. So this is the transition probability, value of the next state, and this is the discount, and together that's how you get an expression for the value of any given state S. Okay, so this is what we just saw, and what's optimal value? Now this is an expression for any value. From this, we define the optimal value as the maximum of the value. So the optimal value, V star of S, is max over all possible actions. RSA plus gamma of this. When you try to maximize this, that's the optimal value. And what's the optimal policy? Pi star S is the argmax. You are doing the maximization again with respect to all possible actions. What will maximize this total reward signal, which is comprised of the immediate reinforcement signal plus discounted future reward. And what maximizes this is the optimal policy. I think we're getting a little vaguer here, but let me proceed. At least you get something. So the basic algorithm to learn this, so the goal is to learn the optimal policy. And in the process of learning the optimal policy, you have to find the optimal value of each state. And so this is the basic value iteration algorithm. There's another algorithm, the policy iteration algorithm. Value iteration and policy iteration. I'm not getting into policy iteration, but value iteration. So what we do is we initialize randomly or to 0 all values of all the states. And then we repeat this is a loop, and so for each state we iterate through all possible state and we apply this equation, and gradually what will happen is the values of the state will increase and converge to their optimal values. An example will actually make it even clearer. And then what we do is once we have the optimal values of every possible state, then we can extract the optimal policy. An example will make it clearer. Okay, so this is value iteration. Maybe let me go to value iteration. Okay, this is another small example. And it's a maze. And this is a robot navigation task. A robot starts from here, and it has to reach the goal state. The state is not the entire state of the board this time. The state is the position of the robot. Okay, so the initial state would be here, and the final state is this. And the robot has to reach the goal state as quickly as possible. And meanwhile, these squares are forbidden. So the robot should not enter this region. Okay, so one possible path is like this. It could go like this too, or it can take a more topsy-turvy path. Now, what happens is when we apply value iteration, now we apply initialize this to 0. This is the starting state. We assign a value of 100 to the goal state. Let's say that's the highest. And we assign minus 100 to all these forbidden states. Okay, and then what happens? Value iteration will iterate through all possible squares like this. And all these, mind you, although I haven't written down what these values are, they're all 100. After one iteration, now we have 4 possible actions: east, west, north, and south. Okay, and let's say the discount is 0.9. Then what happens is, each time, all of these, remember, all of these are zeros. We have initialized all of these to zeros. Now this one, what we'll do is, when we are recomputing this value, we'll maximize over all possible actions, right? So if the action is north, then what happens? We go to a state with a value of 0. If we take east, then we'll end up here with a value of 0. On the other hand, we are, again, I repeat, we are maximizing with respect to all possible actions. So if we consider the action south, we are getting to 100. And that's giving us the highest possible value, right? So this highest possible value times this discount will give you 90. 0.9 times 100 is 90. And so that's the value. 90 is the value of that particular state. This is after one pass of value iteration. After another pass of value iteration, we again update these values. All of these, everywhere, consider this cell here. Everywhere you go, you land up with a value of 0. So this is going to, this cell, the value is going to remain at 0 for now during this iteration. But this and this, from here, you see that if you move east, then you land up with a value of 90, right? So 90 discounted with 0.9 is 81, and the value of this is 81. The value of this, likewise, is 81. you are maximizing with respect to the actions. Next iteration, what will happen is these values will be updated. So this is one step away from 81, right? And so 81 multiplied with 0.9 is 72.9. So these states acquire values of 72.9 and so on. And after you're finished, then you'll get non-zero values for all these states. And then how do you find the optimal policy? Once the algorithm has found the optimal values, then what happens is all you have to do is, okay, let's say you're here. Should you go this way or this way or this way? How do you decide? Whichever one takes you to highest value, which is 20. And so this is what happens. You define the optimal path. Now, in this particular example, it's very simple, and I've never considered the instantaneous reinforcement signal, mind you. But nevertheless, I hope this explains a little bit, gives you a better idea of what value iteration is. The problem with value iteration is this. You are iterating through all possible states. So each time you are iterating through all possible states. Now, you cannot apply this algorithm to a real-world task. For instance, if you had a real robot, what you would like this robot to do is somehow explore, go round and round everywhere, and eventually reach the goal state. Then come back to the state, and somehow from this experience it will learn gradually that this is the optimal path. And that's not what's happening with value iteration. So value iteration is a offline algorithm. It's not an online algorithm, and moreover, in the simplest possible formulation, you also require a knowledge of, you also require these transition probabilities. So you need prior knowledge of the transition probabilities, and you have to repeat, go through each and every state. So it's not possible to do it in a real world situation where you have a robot that is actually moving around. A robot is not going to go cyclically through all possible states, right? So popular online learning algorithm is called Q-learning. So Q-learning, in Q-learning, how much time do we have?
It's 10:35.
How much time do we have for this before? 10 minutes. Okay, let's do it this way. Let me skip the Q-learning algorithm. All I can say is the Q-learning algorithm is really simple. And I'll just give you, just like this example, what Q-learning does is like this. We start off with the same situation as before. So the forbidden states are assigned a negative 100. The goal is plus 100, and the starting state is 0. And the discount is 0.9, and the actions are east, west, north, and south. And first iteration, this is what the robot actually did. It randomly took this path. And then, at the end, once it reaches this, it remembers the path that it took. And then it assigns 90, then 81, then 72, then 65, and so on. To these. Okay. After one round. Then it starts again. And then it reassigns value. Now here you see this is 65. In reality, this should have been what? 81, right? So in the next iteration, let's say it took another path, and then it went this way. This state and this state and this state. Then it'll see that, okay, the previous value that was assigned to this was 65. The new value is 81. The highest of the two is 81. So it will update this to 81. And that's how it proceeds. And that's Q-learning. What I will do in the last, this is actually quite important. Let me still give you an example application. This is a defense project of mine with 3 other people. So we have this defense project. And what happens is this is a military warship. It's an all-electric ship. That's the US Navy is working on all-electric ships. And so there are 2 generators at two ends of the ship, and then AC generators, they're converted to DC, and these are two buses. There are two buses on both sides of the ship, the port side and the starboard side. And this is the electrical grid. So what happens is, you see all these triangles. There are two kinds of triangles here. These empty triangles are non-vital loads. Okay, so they're like air conditioning or lighting and other things, which are not very important. And this, so these filled triangles are critical loads. They're like weapon systems. So what happens is, the reason for this topology is this. Now, once there is this ship is attacked, then let's say this side is bombed. This grid is, there's a fault on this grid because of an attack on this side. So this side, these non-vital and semi-vital loads will not receive any power. But this side will. Now, you see there's a switch here. So one of these two switches has to be turned on. Okay, so this is a vital load. This vital load, you need to ensure that the vital load receives power. So it can be from here or here, either side. So if this side is destroyed, then the vital load, this switch will turn on and the vital load will still receive power. So in order to make sure that the vital load receives power, no matter what, we have this arrangement. Two switches. Each vital load is surrounded by two switches. And one of these switches has to be turned on and the other one turned off. Okay? So what happens is, okay, now once there is damage to the vessel due to enemy attack or something, so there will be faults. And you have to reconfigure this grid by turning on the switches. Off and on, you have to somehow manipulate the switches so that, make sure that the vital loads receive maximum power, because it could be weapon systems that the vital loads would have. And the weapon system, you need to counter-attack. Okay, and so what, so we must, so this is the problem that we have. We must restore power to all the loads during faults, but how do we reconfigure, how do we restore power? By reconfiguring the switches, so throwing the switches off and on under certain constraints, and we prioritize the vital loads. So we have vital loads, semi-vital and non-vital loads, and this is summation of PV, all the summation of the power requirement of all the vital loads, and this weight is actually 100 times of the other weight, so it's weighted much higher. And so this is the total load, and our goal is to maximize the total load that is delivered. So we need to reconfigure the switches so that this is maximized. Now, since it's a question of reconfiguring the switches, why not use a GA, a genetic algorithm? A genetic algorithm would give you the best possible optimal configuration. Now, the answer is this. A GA, okay, this is the starting configuration. This is the starting configuration, and we have faults. But a GA will simply give you the static topology. It will not give you, now what happens is, this is a ship, and a ship has a very small power system. Each time you turn off or turn on a switch, there are transients, right? And if you turn off multiple switches or switches in quick succession, then the whole power grid will become unstable. It's such a small system. It's not like a terrestrial system, which is much bigger. So what happens is, once you manipulate one switch, then you need to wait for the transitions to die down. Then you will operate the next switch, and then the next switch, and so on, until you get to the goal state. So now we have not only a final goal state to arrive at, and the goal state is what? The one which will give you the final, maximize the weighted load delivered, which was this. The goal state is the one that maximizes this. But we also need to go to the goal state as quickly as possible. And let me remind you of our simple problem here. Now this is starting state, this is a goal state. One way to reach the goal state is like this, but that's not optimal. The quickest way to reach the goal state is like this, right? And so what happens is Q-learning here, we use Q-learning. The reinforcement signal is, okay, what are the states? States are, if there are n switches, each pair of switches, one needs to be turned on and the other one needs to be turned off, right? So we have actually, the total number of states is 2 to the power of n over 2, n divided by 2. The number of actions is n, the number of switches. Each action is a turning off or turning on of a switch. So those are the actions. And the reinforcement signal here, the way we define the reinforcement signal is, okay, this is state comma A, and this is the increment in the load delivered. This is L. Okay, so you take the difference of the previous state, load delivered in the previous state, and the next state, and that difference. So this is one term of the reinforcement signal, and the other term is, let's ignore this, this is minus of the time delay. The second expression gives you the time delay, and so this is the reinforcement. So even if you're able to step up the load delivered by a larger amount, if the time taken is large, then effective reinforcement signal is less. And so based on this, we were able to produce an algorithm that would reconfigure the warship in the quickest possible manner to get to a state with where all the vital loads are ensured of power, and the other loads also get as much power as possible. So this is one application of reinforcement learning. And this would be not quite relevant to this audience, but there's a hardware implementation of our algorithm so that you can actually implement it on a machine. So this would be the end of the first part of my talk. There was a MATLAB demo. Maybe the MATLAB demo can wait until the second half.
So now we'll have 15 minutes tea break. So I request all the delegates to finish their tea in allotted time so that we can catch up with the time.
Excuse me, I have one question. Sir, I want to know what are the factors that must be taken into the consideration to maximize the efficiency of agent to decide the optimum policy as well as the optimum values.
The whole purpose of training is to find out the optimal policy. So this is more of a very detailed question. So I would strongly encourage everyone interested to come to me after this talk is over, so we can discuss it in further details. I have a MATLAB simulation. You can look into the MATLAB simulation, and hopefully from my website I can download other simulations if you're interested. But I strongly encourage anyone to come to me and ask questions. Will be with any support.
Thank you, sir.
The initial state, you can start either from left to right or right to left, sir. So, transition state from right to left or left to right.
In which example? A grid robot navigation example.
Reinforcement. Prior to that one, you have shown that supervised and unsupervised. Reinforcement.
Okay.
At any moment, okay, sir. At any moment, it may start the action. Here it has shown that we're from left to right. So it is the action.
Yeah, so what I'm doing here is this is expected reinforcement when you are starting from L.
Yes, sir. From.
Okay.
Yes, sir. So that's okay, sir. That's all okay. But
And
once
you
the
separately
action,
have to follow expected reinforcement from.
so okay, sir. Those are all okay, sir. So those are all okay. Once the state was started and ignited the second one, that means right one, the right one will also start to come into picture, and it will also.
Hold on. Okay, so.
Now you are saying that one.
Here we are considering transitions from left to right. Yes.
So it is having a circularity, supervisor and unsupervised.
No. It's reinforcement learning.
Reinforcement learning between that one and outside from the R also.
Yeah.
So at the same moment, once the R will be ignited by the left hand, so R will also start the same one. So then the action will be ignited more, and the regenerative process will be very fast compared to this a single policy. We are taking the multiple policies at a time.
No. A policy, what you call a multiple policy is actually multiple actions. That is the policy. So the policy is a single policy.
Policy will be a single policy. Once we are considering of left and right.
Remember, a policy is a mapping from a set of states to set of actions. So given L, you have optimal policy. Given R, you have optimal action, and given R, you have.
I have given that. Actually, immediately you will also use. So again the process will start in the R onwards. That means it's not even similar to a circular class. So once you both were coming into picture, the reasonable action will be compared to seeing only left to right or right to left.
No, maybe you're thinking that L and R are part of our agents. No, they are states of the environment. Not L and R. They're not. It's a single agent. So the environment can be in two states, L and R.
So once the R gets included with the L in R.
So once you're in state R. Yeah, maybe we'll.